Hi and welcome to Similarity Video 1. In this video we're going to review the concept of similarity, particularly as it relates to triangles, and we'll consider briefly the mathematical requirements to show similarity through an example. Now, similarity relates to triangles in the context of the Year 10 curriculum and in the lead into trigonometry, but similarity really is a concept for all shapes. And to be similar means that you have two shapes that are exactly the same as each other, except that one is an enlargement of the other. So one is a bigger version of the other. Or, on the flip side, one is a smaller version of the other. And that's what similarity is. And it can be any shape that holds these properties. But let's talk particularly about triangles. So here is an example of two similar triangles. Let's talk about the main features of similar triangles. First of all, you'll have three pairs of equivalent angles. So you can see here that this is orientated correctly, and clearly those equivalent angles are there. Angle A equals angle P, angle B equals angle Q, and angle C equals angle R, as represented by the symbology within the triangle. But secondly, we also have three pairs of sides in ratio. And what I mean by sides in ratio is this side AB and this side PQ are equivalent sides, and you can see that PQ is twice as big as AB. And equally, you can see that QR is twice as big as BC, and RP is twice as big as AC. So we have this idea of opposite sides are in equivalent ratios. And they're the two main features that we get when we talk about similar triangles. So let's have a look at another situation and how we can use similar triangles to help us. So here is another example, and I'll call this diagram 2. You'll see there's some information on a set of triangles. Now, first of all, we may want to show that two triangles are similar. So I'm going to do this in this case. Let's say we label our triangles A, B, C, D, and E. And in this particular triangle, we can clearly state that angle BAC is equal to angle CDE, because they're both equal to 90 degrees, and this is a given statement. So that's given to us in the diagram. Equally, angle BCA is equal to angle DCE, and in this case it's also given, or you could say it's vertically opposite, but because they're given as the symbols, we can say that it's a given statement here. Last of all, we have angle ABC is equal to angle DEC, and this is clearly true because the angle sum of a triangle is 180 degrees. So if the other two pairs of angles are equal, well then these two must also be equal. We don't really need to state the third one. Once we have two, it works. And now we can say that triangle ABC is similar to triangle DEC. And there's our similarity proof. And because we have that similarity proof, it means that we can form a proportionate relationship between equivalent sides. So let's have a look at, first of all, the sides that exist between the two vertically opposite angles and the two right angles. They are equivalent sides, and in this case they are the side 3 and the side 12. So DC over AC is equal to 12 over 3, which is equal to 4. So we can state that triangle 2, the second, the bigger triangle, DCE, is 4 times as big as ABC, and that ratio works. But equally, we can write the ratio out in full. So we can write out that our unknown side, BC, we can write that as BC over EC. So they are equivalent sides adjacent to the yellow angle and the unknown angle in the other corner. And they are equal to AC over DC. Y over EC, which is 15, is equal to 3 over 12. And so we get Y is equal to 3 over 12 times 15, which is equal to 3.75, or 3 3/4. So we can use the idea of similarity and therefore the proportionate sides to calculate missing sides. There are 4 ways we can show similarity, and here are the 4 ways. First, we can show that the angles are all in equal pairs, so the triangles are equiangular. That's one way. The second method we can use is to show that all three pairs of sides are in equivalent ratios. So we have, as in diagram 1, we have AB over PQ equals BC over QR equals AC over AR. We can also show that there is two pairs of sides in equivalent ratios, and the included angle is also equal. So the example would be here in that first triangle is that if this side and this side were in ratio, this side and this side, and then the included angle, which would be the one in the middle, has to be equal. And that would be SAS. And lastly, and pretty much least common, would be RHS. And you can see that this may be an example of RHS, where you have a right angle, and then you have the hypotenuse and some other side in proportion. So as long as you get that right angle, then it can be any two other sides as long as one of them is a hypotenuse. And if one of them isn't a hypotenuse, then you've got SAS anyway. So there you have it. Similar triangles, the ways you can show similarity, an example of how to show similarity, and some of the basic principles. Good luck.